I want to start by actually showing you the way we use machine learning in particle physics. I'm going to talk about applications and why, tell you a little bit about what we do so you can have a little bit of idea of what this is about in our field and where we use it. And then in the second part, we'll go back to the lecture and tutorial part and then you get a chance to do some more practical things. Yep, sounds good? Okay, so in particle physics, right? So I know most of you are not particle physicists, so I'll tell you just a little bit about why machine learning is useful and why do we need this in particle physics in the first place. So I can tell you that it's already at the forefront of what we do. So most of the algorithms that are state-of-the-art and what we do actually rely on machine learning. Now, what sort of stuff we do? We try to find physics objects. We try to identify different types of events. And figure out whether there's new physics or not. That's the main idea. We're after new physics, right? And then the other thing is we're trying to figure out, once we find different objects, we try to figure out their properties, right? That's the name of the game. And as you know, recently, already 6 years ago almost, we found this very nice new particle called the Higgs boson. We're busy, now that we found it, we've been busy characterizing it, figure out if it behaves as it should. And that in itself is a significant challenge. But in the end, we're also after new physics. But in all of these things, machine learning plays a very big role. That's the idea. So how many of you heard about the Large Hadron Collider? Most of you? Some of you? Okay, some of you. All right, I'll tell you about it. So it's really our flagship project, right, in particle physics. So it's located in Switzerland. Actually, Switzerland and France. Here's the border between the two countries. You have the Alps over there, and Lake Geneva. Beautiful place, wonderful place to go skiing, but also a great place for particle physics. So here you see there is a nice ring, so all this happens underground. And there is where we accelerate the particles. We accelerate protons to almost the speed of light, and then we smash them billions of times and billions of times and billions and billions and billions and billions more times. And we smash them in specific places. So we have beams circulating in opposite directions. And then we smash them in different spots. So here there is an experiment called the Cms Experiment. That's the experiment which I am a part of. But then there's also other experiments like Atlas, the other guys across the ring. Then you also have Alice. NUM has a very nice group in Alice. But actually, the pronunciation of this is unclear. Some people say Alice, others say Alice. Depends where you're from. But anyway, there's also LHCb, which is another experiment. And they're all looking for different things. So Atlas and CMS are experiments that just look for everything, right? They look for any new stuff. And these are the experiments that have found the Higgs boson and are looking for dark matter and so on. Now, other experiments, they also look into different times in the history of our universe, try to understand if we can recreate some of the conditions, maybe understand some of these basic building blocks of matter that have led us to where we are today. Now, we've been operating since 2010, and it's a big deal because this thing took 30 years to design, construct. It really is, the world wonder of technology of today. And we're running right now, with this spring, we're taking more data. And it's a huge international collaboration, thousands of scientists. So let's say Atlas and CMS, which are the big experiments, they each have, 3,000 or 4,000 authors, and all of them are students, engineers, physicists, professors, everybody. So it's a big, big community. But one thing I want to point out is in those thousands of physicists that work on the Large Hadron Collider, I can tell you that there is a very significant number of them also work on machine learning stuff for Hadron Collider. So we're talking, the order of, we have a machine learning group for the Large Hadron Collider, which involves all the experiments, and the number of participants in this group has, recently reached something like 700. So you can tell it tells you the size of our community. It tells you the amount of things we can do. So anyway, so 17 miles. Okay, I should switch that to kilometers anyway. 27 kilometers in circumference. Here you get sort of like the view from the underground, and you can see it's sort of where things happen. So here's my experiment, and it's very exciting to work on this. To give you an idea of the scales, right? There's just a little piece. Not a little piece, but being sort of, guided towards its final place. And to give you another idea of the scales, here is a person. This is the Atlas experiment. This is the biggest one in size. You can see it's pretty huge. And here's a picture of the CMS one. By the way, the letter C in CMS stands for compact. So this is what we particle physicists like to think about as compact, right? It is pretty compact, actually. It has, you know, hundreds of millions of channels and wires, and they all have to work in the right way, and tons of components. And it has to be precisely positioned to the millimeter, you know, for the things to work correctly. So in some cases, even less. So anyway. Now, I talked about this discovery. This was a big deal, and it still is a big deal, and we're still working quite a bit. So these guys down there who predicted the Higgs boson have gotten the Nobel Prize. And as I mentioned yesterday, you know, this is the particle which is, you know, they actually explain the mechanism how other particles can obtain mass. A big deal in itself. It was predicted 50 years, more than 50 years ago. More than 50 years ago. And it took that long for society to catch up to build a machine powerful enough to go up to the energy high enough to be able to probe the existence of this particle, and we found it. But the interesting thing is that, you know, machine learning algorithms, even then, nowadays we've moved way past that now, but even then they were part of this discovery, and without it we wouldn't see it, or we wouldn't see it as quickly. That's the basic idea. Machine learning is like a tool which allows you to, you know, kind of like I don't know, glasses or a telescope or a microscope. It allows you to peer deeper, look further with the same information that you receive from nature. That's the idea. So basically, you know, these bumps that you see that correspond to the Higgs boson, that's the original discovery plots from Atlas and CMS, you wouldn't actually see them if you didn't apply machine learning. So their backgrounds would be, you know, it would be hard to dig it out from that background. And I'll tell you a little bit more about that. But anyway, this is like a typical Higgs event, you know, just have to show you for publicity. And anyway, so there's 2 photons coming out from the interaction point. It's a very clean signature. But even there, finding each photon, measuring its energy properly, and identifying, you know, this particular event from the backgrounds also took some work. Now, in the Higgs discovery, I'm going to only talk about the CMS part, since I'm from CMS. I will tell you that, you know, even in those days, even those 6 years ago, you know, this was sort of new ideas. But anyway, at the time, we used it to identify the particles, to identify the interactions where this happened. We also use machine learning for regression, to estimate continuous parameters. So in this case, we estimate the energy of the photon using machine learning methods, more accurately than any other method. That's the beauty of it. And then also, of course, to globally select events. So that means pick events that are, you know, more like a Higgs versus events that look like they would be a Higgs in this sort of environment. So, and each one of these led to some sort of improvement. But if you removed all this, there would be no bump. You wouldn't be able to see it. So, and we wouldn't be able to claim discovery so quickly. So that's the point. Now, what are the general applications? As we talked about the other day, one of the big applications of machine learning is classification. That means, you know, assigning categories to things, classifying them, right? So we use them to identify the particles, to do some pattern recognition. As you could have seen over here, you know, we have all these, you know, tracks that basically particles, as they interact with the detectors, you know, you can actually trace where they go. Sometimes you got fake tracks, real tracks, so tracking in itself is a problem that machine learning is currently being applied to. But the nice thing is that, you know, we have a ton of these tracks. By the way, this is a very clean-looking event, trust me. We've got sometimes a lot more tracks than that. And the point is that we use it to do that more quickly and more accurately. And but this is a pattern recognition problem, right? The tracks. And the other stuff is there's other types of particles, you know, like little quarks start these streams, jets, you know, these stream fountains of stuff going forward, you know, we call them jets. And inside of some of these jets, you also have other particles, and others we call it substructure. You know, so we use these machine learning algorithms to identify such events, and also to improve actually the measurements of all the different objects that we see, from jets to muons to photons. I don't think there's any particle that has been touched by a machine learning algorithm in the last few years. But also we look for, like in the big picture, we use it to search for new physics. So basically use it to identify interesting events, new events, look for unknown things. And, but then other things like how to monitor the quality of the data, right? Because we have a ton of detectors, right? And we have to, we actually babysit them 24/7. There's people on shift sitting around doing shifts, physicists and engineers, and making sure the detector is working when we're taking data. right? And that means also monitoring the quality of the data as the data comes in, looking for problems, trying to predict problems before they happen, and identify them early, and that's where machine learning is also used nowadays. Other parts, like also how we move our data efficiently and all sorts of computing questions, there's also applications in that, but I won't go into that part. The other piece outside of classification I mentioned briefly is this idea of function estimation. And this is important because we want to measure particle properties. We want to be able to measure their masses better, their energies better, all sorts of things like that. And for this, we use same machine learning algorithms, but with a different target, right? Remember, for classification, we had multiple classes. By the way, it doesn't have to be 2. You could have more than 2 classes. In fact, many problems do have such a case because we have many processes that produce, lots of different types of physics. And sometimes you want to be able to discriminate between them. So we also apply multi-class classification for them. But in this case, what you apply in the case of function estimation, the output in this case, you only have a single output or sometimes multiple outputs. But here, you're trying to approximate some continuous function, right? Like temperature or humidity. In our case, it's could be energy. Right? Any questions so far? Make sense? Good. All right, well, let's talk about challenges, right? And it's not all rosy in everywhere. So I'll tell you what our challenges are and today and what they are going forward and why actually machine learning helps us and all that. So one major challenge is that if you look at this logarithmic plot, which should tell you how multi-scale our problems are, here it's, you can think of this, we call cross-section, and it's basically a probability. So anytime we collide our 2 protons or some other particles, right? It's a probabilistic thing, right? It's like a lottery, right? So out of that pure energy of that collision, you can make stuff, right? And what you make, right, is there is there's different probabilities of making different things. So imagine if you were had a bunch of energy, collided stuff, and the probability of making let's say an ant, and ants could be pretty common. Making a dinosaur, be a little less common, right? So there is a question. So all of these processes, all the different processes that we observe, have a different probability of occurrence, right? And we measure that. So this is like the total probability, and then let's say here is the probability of the bottom quark. Let's say one of the particles that is fairly common to produce. But then when you start going down here, you see these are orders of magnitude down. They start producing, different bosons and the W and the Z. The top quark is down here. But then, you see, this is the stuff, this is the Higgs. That's the stuff we already found. You see how improbable it is to make it compared to everything else that we make, right? So what we're really after are like little tiny needles and huge gazillions of haystacks, right? Now, we've already had some success to find it, so I can tell you that we are pretty good at this part. The trouble is that the stuff that we're after now, the stuff that we want to measure, like maybe do some precision measurement of the Higgs, and then sometimes multiple Higgs production, things like that. Or even look for things that are like dark matter, which are down here, right? It's an enormous challenge because the backgrounds are orders of magnitude higher, right? And for this purpose, machine learning is a big deal because it helps us isolate those specific signals as opposed to things that look like them, right? But that's a major challenge for us. So not to be understated. The other challenge is that we're actually going to make things harder for ourselves. Well, why would we make things harder for ourselves? So remember that nice looking clean event I kind of showed you earlier? Well, our events are going to look like this very soon. Why? Because we want to have more data. Right? We want to have more data. So what does that mean? One way we can have more data. So one way you can prove new physics is by increasing the energy, right, of the collision. And right now we're really at like the max that we've gotten so far, right? So the Large Hadron Collider is basically an order of magnitude, higher energy collision than let's say its previous instances of such colliders. Now, one way you can do things is increase the energy, right? And then you can probe new things. But if you just want to collect more data and improve the statistics of your measurements and just sort of look for new things just by adding more data, then the other thing you can do is actually squeeze more collisions, right, per unit time. So that's the idea. The idea is that we're going to go to something called high luminosity, and that means we're going to be colliding more and more particles at the same time. We're going to squeeze in more of these guys inside of the ring, and we're going to collide more of them. But unfortunately, that comes with a problem. As you know, as you living in Mexico City, you're all, I guess, pretty familiar with traffic, right? And this is really the problem of traffic, right? This is something called pileup, when you have cars coming behind you, and then try, so in our case, these are collisions that are happening, that are coming even from behind, but you already start to see them, right? Because they're all so bunched up in that one little ring. So we're going, an order of magnitude increase in traffic. And that means also an order of magnitude increase in all the different particles flying around. So imagine the challenge of finding the things that you want in all of that debris flying around, right? And the interesting thing is that the more complicated the problem, the worse our sort of conventional algorithms work, but the better actually for the machine learning ones, because they are meant to, to help us solve these more complicated challenges. So the more complicated, the greater the separation, actually. So it's a good case for machine learning. Now, the other thing I haven't mentioned is that, for example, the CMS experiment, also the Atlas experiment, some of the others, we have something called the trigger. The reason we have a system, an actual hardware plus software system, it's like an event selection, event filtering system. The trouble is that we have so many collisions, right? If we were to save the whole information from all the collisions, there would be not enough space on this planet, maybe a few other planets. So we're actually forced to throw away 99.9 some high percentage of all of our data. We never see it. It goes in, it goes out. And that means that when we start with something like a 40 megahertz rate, after going through the electronics, special electronics sitting on the detector, sitting right there, where the data comes in, we reduce it to 100 kilohertz, and then in the software level, we also reduce it to about 100 hertz. You see, that's the stuff we actually analyze, publish papers on. That's the stuff that's coming in. So what does that mean? That means that A, we have to do a very good job in a very, very short time, less than a microsecond, to decide whether what comes in is interesting or not. Because remember, garbage in, garbage out. You save garbage, you're not going to do good physics. So the better you do at this first level, the better it is overall. So that's a major challenge. Why? Because in that very short time that you have this event, you have to decide. You don't have time to reconstruct the whole thing. You don't have time. You don't have the full information from all the detectors. You have to make the decision based on incomplete information, right? Oh, is there like an interesting particle that went that way? An energy imbalance over there. So you have to use some kind of handle, some sort of tricks to narrow this down. And the interesting thing is that now, for example, the CMS experiment has already machine learning algorithms in the hardware at this level. Oh, sorry, I went a little too far. So we already put some machine learning algorithms in there for very specific purposes, to better estimate the momentum of a certain particle or so on. We haven't really put everything. We're starting to put more and more sophisticated things in the trigger here. Because why would you do that? Because if you do a good job here, you'll do a great job there. And we already see that by putting machine learning algorithms, we're able to do better physics, select events better. Now, other experiments also have put more machine learning on this level. But at this point, you've already lost a lot of data. But to give you some ideas, and this is forward-looking ideas, this is sort of future. This is not present yet, it's future. One of the future ideas is actually to put machine learning, some of the machine learning algorithms here, and do something more than just simple classification, right? So the idea is that even though we cannot keep this data, it may be possible that we may be able to actually learn from it as it passes through our hands, right? And maybe it will guide us towards, maybe there is unknown physics or unknown things that otherwise we would lose because we just simply throw that data away. So this is some of these newer applications that I'm talking about. But anyway, so the interesting challenge here, a related challenge, you may think machine learning, right, it's all in software and algorithms. No, right? You actually have to, in some cases, like self-driving cars or whatever else, you have to put that right on the hardware itself, right? And in our case, we have that challenge that we want this to work in real time. By the way, all of you have cell phones, right? Well, machine learning algorithms are coming to your cell phones because both Apple and Google's, they've already made the chips powerful enough and the software powerful enough to be able to do it. So the next generations of, basically the next generations of our phones are going to have machine learning algorithms running on them, right? Which opens up a lot of sort of like real-time applications. For us, it's a problem already, so we've been already doing this. So. Okay, but be aware that you're going to have your phones. You'll be able to maybe run some of these algorithms on your phones pretty soon. So, okay, now what are our upcoming challenges? We have a ton of challenges as particle physicists. One of the biggest ones is that in terms of the LHC, that's how much data we intend to accumulate over the lifetime of LHC. It's an enormous amount of data. Our resources are not going to go up that fast, computing-wise. We have to do more with less, right? And the other part is that, as you may have heard about, we actually have no idea about this kind of an old, actually, distribution. But anyway, most of the stuff in the universe, we have no idea what it is. So there's some unknown physics. So we have to also be on the lookout for stuff that we don't know. So you have to be flexible enough to be able to find these things if they show up in the data. And one of the big deals, of course, is the dark matter, which we know it exists. We don't really know what it is. If it's a particle, we hope to find it. Something that I'm working on in addition to the Higgs stuff. So anyway, what are the interesting areas when it comes to machine learning? Well, tracking is a big deal, right? Because it's a problem that we have. It's a very useful thing, and we use it a lot in analysis. So finding tracks, finding these patterns, that's a major application. Identifying objects. Is this a photon? Is this an electron? Is this object or another? Or is it some other object that looks like it? That's one of the challenges, object identification. Event filtering, the trigger thing I just told you about, right? This real-time thing, that's another big challenge. We use all these imaging techniques and so forth. That's sort of nice thing because now we can explain, we can actually pose our problems as image problems sometimes, and then you can use techniques from computer vision and so on. Simulation is a big deal because most of our computing budget actually goes into simulation. More than half, actually. And why is that? Because we have a pretty good model, this sort of called standard model of particle physics. We have a pretty decent model of how we think things should be, right? The ones we know is very precise. And we have a first principles idea how it works, so we actually can simulate it. We do Monte Carlo simulations of that model, and then we also have models how these different particles interact with the detector. We have software that does that. Unfortunately, it takes too long. It's really long, but there's no easy shortcut because you have to really, make the particles, have them simulate how they're going to interact with the detector, and then we have to figure out what it is that we're going to be seeing. But it's very important because we want to claim that we found something new. We want to be able to say, look, we understand what's happening, right? So for us, it's very important to have these simulations. Now, the good news is that machine learning has provided us with a shortcut here because we can actually bypass all of that, simulation piece by actually learning the output of that simulation. You can go straight to the output and say, look, this is my input, here's my output, can I learn and skip the piece in between? Now, learning takes time, but applying it doesn't. So that means when you come to the stage when you have to go and simulate these events, if you've learned it, well, then you just basically go, I'm going to go apply my model, I'm all done trained, and that's 3-4 orders of magnitude faster than what we're currently doing, which is why there's a ton of recent applications in simulation. Okay, and just to give you, for those of you more familiar with machine learning terms, I'll just, for the same problems, I'll put some of the algorithms that are used. So for example, here we use machine learning with FPGAs for sort of real-time machine learning. Here you use deep Kalman filters, recurrent neural networks, LSTMs, that stands for long-term, short-term memory networks. And for the simulation piece, this is where we use generative models, adversarial networks, etc. And for the object identification, we use everything, right? So from recurrent, LSTMs, fully connected, whatever. The other part that's interesting is this multi-objective piece because oftentimes we actually have multiple functions we need to estimate, and that's why that's a relevant part. Convolutional networks are all over the place, especially whenever the problems can be expressed as imaging problems. So again, for all these different challenges that we have, we try to apply the more appropriate models, right? So, any questions so far? No, good. Okay, so just sort of to recap, these are sort of the challenges that we have, and this is where these things apply really well. And I can tell you that in all of these areas, these methods have gone from being sort of R&D to sort of state of the art. So they are outperforming any other method that we have come up with in this area. So what are some of the questions? Now I talked about big picture questions, right? Or like particle physics challenges and stuff. But let me actually now talk about more of like what are the questions when it comes to machine learning applications together with particle physics, right? So now combining those things together, right? Again, zooming in a little bit. So one such question is, how can we actually fully exploit all the information we have in the detectors? Remember, our detectors are huge, right? We've got hundreds of millions of channels. They're not always on at the same time, so they're not always used, because when you have a bunch of tracks going, it's a sparse problem, right? You have tracks here, 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 but in other places you don't, right? So you have just noise. It's a sparse problem. But, as I mentioned, we start with this sort of first principle thing, where we make, different particles, quarks and gluons and other particles and whatnot. Eventually they reach the detector, interact with the detector, and then we read it out and we see what's there. Now, and then we use those particles that we've identified to combine them together somehow and do physics analyses, right? So that's sort of starting at the high level. That's traditional approach, is to actually condense. What we've been trying to do for many, many years is condense all of those hundreds of millions of channels, right? Hundreds of millions of inputs, really to just some sort of one final thing, right? At the end of the analysis, we're looking for the Higgs boson, for the mass. Remember that plot I showed for the Higgs? We were looking for that bump on that mass distribution. In the end, it all boiled down to one single distribution or figure of merit, right, that we use to test whether there is new physics or not. But the interesting thing is that in the old days, people kind of started to, did the analysis starting over here, right, where you've already reconstructed everything, you found all your objects, and then you make some selections, maybe you pick 50 sort of high-level variables. Nowadays, that's not something that we do. Something that we do now is increasingly go from right to left, right? And machine learning allows you to do that. So instead of, sure, you can apply machine learning over here too. You can also, apply all these fancy, whatever, deep neural networks and whatnot, other methods to high-level variables. Oftentimes, even theorists can suggest to use some smart high-level variables to separate your whatever interesting classes. But we've been increasingly going to low and low levels of the data because, as it turns out, the algorithms we have used until now to produce these reconstructed particles and whatnot are lossy, and we have lost some information there. And it turns out that by going lower and lower data, more towards the raw data, by bypassing traditional reconstruction, we're able to regain some of that information that was lost. So that's one of the major sort of questions that's being sort of tackled now. And an example of this, I'll just show you a simple example of this, is where rather than using sort of more high-level features to identify particles in the electromagnetic calorimeter. So for example, you have photons and electrons, and they both induce showers, electromagnetic showers inside of our detector called the calorimeter, which measures the energy. You can actually express that problem as an image problem, right? And then you can see that if you apply, some convolutional type network to this, what you'll see is that you end up with a really, really nice classifier that performs much better than if you used high-level variables like how wide is my shower, how deep is my shower, things like that people have used before. What's interesting is that the performance of this guy, we call it end-to-end learning because it kind of goes in that way, right? End-to-end means you start over here and you do the whole thing with machine learning. That's kind of the idea. But inside of it, there is lots of machine learning in different types in different places. But the idea is that. And the interesting thing is that when you start applying it to physics, the more objects you have, the greater the separation. So for example, when you have 2 photons and 2 electrons, performance goes up even more. When you start having more and more objects, it becomes really powerful. Now, this is just using one detector. Remember, we have a ton of them, right? We have different detectors that look for different things in different particles. You know, we have a tracker that tracks, colorimeter that measures the energies. The muon system measures the muons, which are these, you know, heavy brothers or sisters of the electrons that we think maybe some signal may help us find some new physics. So we also try to use all these different detectors together, that whole, you know, 100 million beast. You know, we're not there yet, by the way. We don't use the raw data yet. Now we're mostly at this part now. We've made it down here, right? We haven't made it there yet, but that's sort of the holy grail for this particular question. Now, I guess one important point to make is that one shouldn't reinvent the wheel, right? So if we can express a problem, or if you have a problem and you can express it as a known problem, you should apply known tools. So for example, if we can express a problem as an image problem, then you can use, you know, obviously techniques from computer vision, like convolutional neural networks, etc., to that problem. And we've had a lot of success doing that. How do you make the problem, because for us, these are not literal images, right? So I can tell you a little bit about how we do that. But anyway, you apply some existing algorithms. If the problem is not solved, then you push the knowledge boundary forward. And we've been doing that in a number of cases. But to give you an idea of how this imaging thing works, this is for an example of using, you know, an early example. This is 2015, I guess. And that uses convolutional neural networks to basically identify different types of jets, right, or substructure within the jets. And you can see, you know, you pose the thing as an image, and you can look at the different filters. You can see what the network is learning. It really learns to pick out the difference when you have sort of two sources of things versus just one, right? So it learns to do that. Like, it learns to pick that out. And in this case, it's, you know, when you have also another, you know, some other physics is happening inside, right? So by eye you can see it, right? Your eye tells you, hey, this looks different, right? But, you know, if you did it the way it was done before, you wouldn't be looking at that. So it uses this image techniques to do that. Neutrino experiments have also gotten pretty good applications out of this. So neutrino experiments, they're basically studying, you know, they're studying very, very special particles, the neutrinos. They're very weird. We know already, thanks to them, we know that there is something out there beyond what we understand, kind of like dark matter in a sense. And the reason is that, you know, they're weird. They can oscillate. They have 3 types, and they can kind of turn into each other and back. And it's a weird thing. And but to study that, you have to observe them. And to observe them, you know, they create these detectors in particular. So this is an experiment called NOVA. There's another experiment called Microboon. The point is that you can see neutrino events. They're actually very, very clean compared to the events from the Large Hadron Collider, right? So in that sense, you can actually see the pattern, and you can pose the problem as an image problem in a very, very natural way. And in fact, the NOVA experiment has shown, you know, a couple of years ago that they were able to, you know, basically improve their analysis by about 30%, which means that, you know, if they ran for 30% longer the experiment, they would have gotten the same result if they didn't use machine learning. So it means that they saved some time and money, let's say. And that's pretty much the case now, both for the Large Hadron Collider and also the Neutrino experiments. That's roughly the orders of magnitude, order of improvement that you're getting. So 30, 40, 50% sometimes in specific tasks. Now, another example is tracking, right? Now, I told you about tracking. I know how many of you actually done like a little experiment, but you can actually visualize sometimes, you know, how these particles go through matter. And you can see that this is something where you care about the history, right? So when we watch, right, it's an interesting thing, by the way. Our own brains, if you think about how we see, let's say a bird flies by, it's quite interesting how we track it, right? It's millions of years of evolution, how we've learned to track. We've learned how to, like, you know, draw the pattern, even though the light hits our eyes and we're following that object, and then we're literally tracking that object. And sometimes, we're able to predict where that object's going to go next a little bit based on where it was doing before, right? So it's something evolutionary. But what's interesting is how our brain does that, right? Based on all the stimuli that it gets, all the inputs it receives, our eyes, basically, right? And the way it works is you also have to sort of pay attention to the state of that object, right? So in this sense, this is a very nice use for, for basically types of deep learning that also has the idea of time components. In this case, it's recurrent networks and also these LSTMs, because you have an actual state, memory, that you can propagate, you can track, right? So the interesting thing is that there's a special project which is a collaboration of different experiments, and they've shown really nice results. Actually, I'm not showing you the latest results. The latest results are even better. But they're able to very accurately identify these tracks and do it much faster than any other conventional algorithm. So that's a very, very promising area. Now, another sort of question, right, is how do we make, how do we extract meaning, right, out of the data, the feature extraction piece. And some old studies, actually they're not new, is interesting, is that they showed that, we physicists, right, we also have an army of theorists, really smart people who understand how these models work, and they give suggestions for what are these really good high-level variables. It could be something like a boost into the rest frame of reference of this new particle you're after, and then do some more stuff. But anyway, and that's going to help you to separate what you want from what you don't want. The interesting thing, these are sort of high-level variables, right, sort of high-level things. The interesting thing is that if you give a machine learning algorithm just the low-level data, it does just as well as if you gave it the high-level variables. It means it can actually learn them, it can extract them. You don't even need that theory. Okay, I'm sorry for the theorists in the audience, but for some of these things, you're able to extract that. The question is, can we understand what is being extracted? So far, there's been a lot of interesting findings where these features which are extracted, they actually make physical sense. So these algorithms are actually learning physics. They're learning relativity, they're learning Lorentz invariance, they're learning things that we understand. That's sort of the part that we are lucky, because in some sense we can actually open up these boxes and compare it also with things that we know just because we understand physics, right? Because we know something about the principles of this physics. But it's quite interesting that these algorithms do manage to do it. And that's a difference from where I was maybe 10 years ago, because 10 years ago, or 5 years ago, non-deep learning algorithms like boosted decision trees or so on, they were really, they really required you to engineer those high-level features to do well, right? The new thing maybe with some of the more recent deep learning algorithms, that they're able to extract some of these features as part of the process, right? And that's I think, a very exciting piece. Now, here's a simple example. Remember about pileup and traffic I was talking about, So we have some algorithms that whose whole entire existence and their whole goal is actually to remove that noise from other particles that come from these other collisions, since they're not relevant to what we want. And there they employ basic convolutional networks, for example, to what these things look like. And what they find is that if you actually open up the box, right, and you look at these 3 different channels, with these image things, you have the different filters, red, green, blue, RGB, whatnot, different channels. And what's interesting, when they actually open it up and they look at these different filters that they're doing, when they actually look at it, they see that what it learned is something that a different conventional algorithms have used for years, something linear, something that they understood. But this is just one part of it. So they're able to interpret it, right, and connect it with something they already knew, right? So this algorithm learned something that they already know from physicists. So it learned physics. And there's other examples like this. I won't go to all the examples. There's too many. But what I'll just tell you is that in terms of the questions, in terms of defining the problem, is you want to also figure out how to best use your domain knowledge, right? Because we actually have domain knowledge, and all of you have domain knowledge from your domains. The question is, how do you combine that with these machine learning algorithms? And And the idea is that, sometimes you can actually incorporate that knowledge in the design of the algorithm. That's a really hot area for us. We're actually combining our domain knowledge of particle physics with some of these machine learning algorithms to see if we can end up with better machine learning algorithms. So we're kind of merging the two things together. It's a very exciting area. And to give you an idea, for something like string theory, that we have theorists applying these to look for models within string theory. And in fact, some of these guys have also written papers on Riemann-Boltzmann machines and new machine learning algorithms inspired by quantum field theory, which is something really, really nice. And now it's a pretty big thing, not just in particle physics, but also outside. Now, these images and also these ideas of, from natural language processing, and for us, it also is interesting because you can think of these things as, sometimes you can think of these as sentences, right? For us, the way particles evolve through the detector, right? There's an evolution that happens. So you have, these, we call them jets, right? So you start with one particle and then out comes a whole bunch of stuff, right? It evolves. And the interesting thing is that, what we're doing as physicists is actually going backwards. We're trying to figure out what happened in the beginning. So you try to cluster all the things we see. And it turns out that by applying some of these, recurrent networks and so on, is equivalent to what we've been doing for the longest time in special kinds of clustering algorithms that we've designed to find these jets. So this KT algorithm, for example, has a nice recurrent machine learning algorithm that does it as an equivalent. So the interesting thing is that now we're trying to kind of combine the two things together to go a little bit further. And there are more examples of this, so I won't go into all of that. There's a major area that is a big deal for us. It's always been a big deal for us, and it's starting to become a big deal also for the machine learning community. And it's a question of how well do you understand your data, how well do you understand your results, and how confident you can be in what it is you claim. It's really important to us. For that reason, we've been always worried about uncertainties, all kinds of uncertainties, systematic uncertainties, and the statistical uncertainties and whatnot. And for us, we have so many sources of these. Some of them come from our lack of understanding of the theoretical models, right? Some of them come from measurement. We don't have perfect detectors, so we have uncertainty in the measurements. But then, doing analysis, any kind of analysis, not just using machine learning, also involves introducing some kind of uncertainty. And how do you treat that? And we've had decades and decades of physicists and statisticians who've tried to define ways to deal with that. Now, one of the important questions is, now that we're using a lot of these machine learning models to do some of this decision making, and we use them also to make statements about nature, right? We use them as analysis. We also need to be sure that we understand how do these uncertainties come in, how do you treat them, and then how do you also estimate them, and do you introduce any new ones? Right? It's important to not be biased in all of this. So there's a lot of work that's been put in recently also in particle physics on this uncertainty question. And in fact, there's a conference now, there's a machine learning uncertainty conference, which is a bigger one outside of particle physics. But the point is that they matter. And there's some nice work, so this, for example, a paper by Gilles Loup and company, and that showed that if you completely ignore a systematic uncertainty, even one of them, and you go through the whole sort of process of reconstruction, analysis, you end up with your final classifier, and then you make a decision, right? Remember we talked about yesterday, we talked about the decision boundary, right? You separate your classes. Where do you draw the boundary? Well, it turns out that the place where you make that decision, right? If you just ignore the uncertainty, okay, and you use machine learning models, the place is pretty obvious. However, if you actually put in the uncertainty, even one of them, the optimal decision boundary moves. So what used to be optimal is not optimal anymore. So if you really want to be optimal, to sensitive to new physics, and let's say be more robust to doing things, then you actually have to incorporate them in the models. And how you do that, that's described in some of these papers. Anyway, there is a nice connection to the Bayesian statistics, and that, so this was shown already not a few years ago that actually, these deep networks with dropout actually start approximating this variation in the field. So it's a really nice connection. So, and we have also quite a lot of Bayesians in our community. So we also have Bayesian neural networks and Bayesian many things. So we try to, and that has also a nice way of actually approximating some of this uncertainty. So that's one of the directions to date. Something I mentioned earlier, and I guess I'll put one slide here, but there's a ton of work in this. I would not be able to give it justice here. I'm just showing one example. There's even more recent things since then. It's how we use this generative adversarial networks for simulation. Remember that simulation problem? Inputs, outputs, you try to learn them. So this specific approach, it's actually a new variant of a generative adversarial network that these guys have introduced. It's called Lagan, I don't know how I pronounce that. But anyway, so the idea there is that, you have, the A here is for an adversary. So now you have actually multiple networks, right? So there's a competition between them, and you have one of them you're trying to fool, and the other one tries to fool. And the point is that, these guys have gotten pretty good at you probably have seen, these GANs. In fact, Ian Goodfellow, the guy who invented them, he was giving a recent seminar at CERN, and he was the inventor, so he kind of follows the thing pretty well. But then it turns out that the people in the audience knew some of these things even a little bit better, and he's like, okay, interesting, we should try that next, And it turns out that the community that we have in particle physics have really pushed this application really far. So when it comes to simulating things and applying GANs, we seem to be also one of the leaders today. So if you're interested in simulation, that's the stuff to look at. The other part, which is really interesting, we've been also applying many of these methods to things like flavor tagging. So when you try to figure out the multi-class problem, right? Where you have we have many different kinds of jets, right? And we want to figure out what they are and do analysis. The interesting thing, don't be confused by these plots. These guys use both convolutional networks, recurrent network, dense. They do all sorts of things. There's all sorts of nice stuff under the hood. But the really, really cool thing is that what it really is doing, it's taking a lot of input and it's paring it down, only getting to the most relevant things, and then using those relevant things together with our physics understanding. Like we have this thing called particle flow, which is flows of particles through the detector. And together they achieve unprecedented performance. And what's really interesting is that the improvement that you get from using this. So if you didn't use it, you would be here. If you use it, you would be over there. That's a huge improvement. What's interesting is that that's equivalent to give you a number, the improvement you get from doing this is equivalent to installing a brand new detector, which we did. That's basically the effect of that. A brand new detector that you spent 10 years building and a few $1 million or more constructing. So just by applying the algorithm to the same data, we're able to save yourself millions of dollars in our case. And we're pretty prudent about how we spend our money. So anyway, now there is something else, and the something else is that there's different models, there's different ways you can think of how to solve these models. And the model we found to work really well is this multi-task model. Right? It's instead of building classifiers or whatever else that are very targeting something specific. Let's say we have two kinds of particles and we want to separate them. Oftentimes we don't have two particles; we have many. Right? So instead of building individual classifiers to look at one particular task, what we found is building this multitask model, right? Which, depending on the task and the input, it adapts and changes, but you train the whole thing. And what we found is that this is, even for the case of the individual problem, they work just as well. So we find that having a multitask model is much better than having n single task models, right? And there are examples of that. And obviously the real-time application is a big deal. So for us, for machine learning, this could be used for other things. But for us, it's important for the trigger, this idea of sort of selecting events. And that's one of the major sort of things. And what you see is that for us, when we use these applications, we're able to reduce the rate rate of these triggers, so how often the particles that we don't want, appear, and how often do we keep the ones we don't want. So we've halved that basically by using a machine learning model. And the interesting thing is that we've put out an FPGA. How many of you know what an FPGA is? Okay, some of you know. And but these are devices that you can program, and you can they don't really require any memory or anything like that. So you can actually, if you have an algorithm that's already trained, you can go ahead and put it in there. It's like a bunch of simple if-else sort of logic, right? You can put in there. So decision trees, for example, decision trees are quite natural for these, right? So because they're kind of like if-then-else type of algorithms. So when I told you about the first application that we did in machine learning, that was basically a decision tree, a boosted decision tree, which was implemented on an FPGA, which was sitting on the detector, on the electronics, when this data was coming in, and it was estimating, let's say, the momentum of the muon. It was a regression tree. Now, one of the more recent things that I've seen, I didn't add it here, but I could have, is we actually managed to put much more complicated models on these FPGAs, on modern FPGAs. So we're talking about some of these convolutional networks, fully connected deep learning networks. We managed to do it. Of course, we were not able to put in something like this, million-layer network. Some of these, fancy networks people have used. But we've been able to put in some of those that are relatively complex, pretty well performant, even with the limitations that they have. But I think that's the future. That's the future of real-time learning, and it's a big deal. But also other experiments like Bell and others have put some simple, shallow type networks on their electronics. So it's been done. But I can tell you the direction for us here is we're putting more and more sophisticated models automatically. So by the way, these days you don't have to write the low-level code. There is sort of like high-level code that you can program these things in. You can actually take a model like a C, model in C++ or whatever, or Python even now these days. Or you can convert it to the C model and then use some specialized translation languages like HLS, whatever, that goes and directly puts that in the format that would be understood by the FPGA. The other interesting thing is that here, this particular application used the lookup table. So when you've trained, right, you can make a lookup table, right, once you're done training. Now these things are literally sitting on the FPGA. So you actually have machine learning algorithms on the hardware. What's really interesting is that the next generation of the hardware, it has, on top of all these different gates that you need for the FPGA, it also has a bunch of RAM. So something like a terabyte of RAM, which allows you to push a ton of other operations on it, which allows you to put even more complicated models. And as we have seen, the models are only getting more complicated and bigger. And so, so that's sort of an important consideration. Okay. Now, I just will touch briefly on what are some of the other applications. Now, I haven't mentioned unsupervised learning, right? And that's where you don't have any labels, right? And you're looking for possibly unknown things, so you can use it to see if there's any anomalies in your data, identify if there's problems with the detector, or you can actually look for unexpected physics, right? But there's also other kinds of approaches. You have weakly supervised learning and other things, and transfer learning, reinforcement learning. We do all of that. And all that has applications in many different areas, both in monitoring detectors and also in looking for physics. So that's sort of the applications that people are doing. Now, I mentioned generative models. That's another area. And we use it for simulation, but also for other things. Like you saw, we use these GANs also to figure out how to treat uncertainties and how to even make our classifiers unbiased. Something I didn't mention yet is that sometimes depending what sort of inputs you're working with, you can sometimes build biased classifiers. It's an issue for everyone. And the reason I say bias is because in the end, you want to use these things to do physics, right? And as physicists, we know that there are certain observables that make sense to us, right? So when we look at like the mass of a particle, we know what that is, right? And the interesting thing is that a machine learning model doesn't really know that, but it can learn it. And what's interesting is sometimes you can, depending on what the inputs are, if you give it the information that by accident, right, that the machine learning model should not have learned from, it may even learn to discriminate things based on mass. And you may end up kind of almost like sculpting a peak, where you shouldn't have. So, you can have a completely background-only distribution, but because you've learned how to discriminate things based on some specific thing, like mass, right? If you've introduced that information, let's say, then what you'll end up with is a classifier or a model which is going to be looking exactly there, and it's going to, distort that distribution. So how do you deal with that? It's an important question, and we found, very good ideas on how to do that, which I think are also relevant to other fields. Whoever does analysis and has some sort of to do meaningful hypothesis testing and so on, and you want to ensure that your classifiers are unbiased. And for this one, one can, if you have a question on that, I can point you to a few of the works that have been done. Yep.
You mentioned that when we give the raw data, the basic data to the algorithms, they can learn information, learn transformations, and they basically learn physics, right? But could they learn things that we don't know how that happen? Is that possible?
Yeah. Actually, how about I answer your question when I finish this? Because I have a nice answer to that. So let me finish this, and then I'll go to your question. Optimization and tuning is sort of another thing, with Bayesian and another thing. So this is not another. But there's many applications. But actually, maybe just because I was getting to the end, I'll get to the end, and I'll get to your question. So anyway, I'll just summarize real quick, right? So my summary is these methods are very powerful. And we've really managed to take them from something like R&D to actual production. So nowadays, they are the state-of-the-art for many areas from us, from tracking to physics to particle identification to pileup removal, whatever it is. There's a lot of progress. We have a community, a large community that allows us to not just be, the users, we're also contributors. So we're kind of, in some cases, we're at the front of this area. So we also have some talented people who are not afraid to think big and actually try new things. And so that's part of the progress. And it's a great tool that will help us address, I think, some of our future challenges. To answer your question, I have maybe 4 or 5 examples, but I'll just give you 2. One example was actually all the way here. I was talking about Neutrino Experiments, right? Where was that? Here. So these guys, they trained, and girls, they trained a convolutional network, a multi-class, right? A multi-class network. And what was interesting is that when they looked at their predictions, right? They saw, you can use some visualization methods to try and group some of your, some of the classes together, so, right? And what was quite interesting is they also ended up with one set of events that didn't make sense. Clearly there was some class, right? There was some sort of a class that didn't make sense. And it turned out that there was a mistake in the simulation. They figured out that there was a mistake that everybody missed. And the only way people found it was when they applied these methods. And they said, oh, there's something happening here. What is happening here? They went back and they checked, and they saw there was actually an error in the simulation. So they went back and fixed that. And the problem, went away. But the point is that, but then there are other examples where, and this is a very interesting area, because when you open up the box, right, when you compare like the pileup removal case, for example, or whatnot, there are parts that connect immediately to your understanding of the physics problem, right? And maybe the first order part, but not the second order, right? And the second order, you wonder, well, what is that? And so there are cases like that. Another case is, I guess, when I was talking about these jet images here, or jet substructure. Substructures mean when you have stuff, you have simple jets, and then you have jets with more complicated ones that are more complicated processes. So they have other particles inside of them, complicated particles, and like W boson in there or something like that. What's interesting is that theorists have come up with some of these really fancy, complicated, high-level variables that help discriminate the two, right? I won't tell you the names. It only matter if you're doing this. What's interesting is that when they've built these machine learning algorithms and they went to see what are they learning, right? And you can always project the output of your network or whatever classifier also onto these variables, on these high-level variables, and see whether the two classes look different there, right? And what they saw that in fact, what this network was learning was in fact some of these high-level features, which were produced by the theorists. But that wasn't all. So there were other things that they didn't know what that was. So anyway, so that in our case, it's actually a really good thing because it does potentially help you find new, new ideas and also new physics understanding. But there is maybe a bunch of examples of that already. Maybe I'll stop here and I'll let you ask some questions. Yeah. Yep. To incorporate the new, what? Yeah. Okay.
Is there any maybe way to put this in a training?
Let me see if I understood your question. What you're saying is that, let's say you built a model that, I don't know, let's say finds out how to, I don't know, how to classify the Higgs, right? So you built a Higgs classifier, right? And then you're asking, can I then use that Higgs classifier to look for new things, saying that's a Higgs? Of course, yeah, of course. And that's something that we do. For example, whenever we build something like, let's see, where did I have that? I had it here, I think, somewhere. Yeah, so let's say we build a new flavor tagger, like flavor tag. So for example, like a B tagging. We have this special, so B quarks are important, right, for us, because there's different ways that other new physics can decay, and one of the signatures was going to have some of these B quarks. So the reason they're interesting is that because you also have, they also have something interesting to them, is that some of them, they have a lifetime, so it means that they decay a little bit further away. So they don't. So you can find it a little bit away from where all the other things are, and you can measure that. So we have algorithms that actually look specifically for these Bs, the so-called B tagging algorithms. This guy here is an all tagging algorithm, so it tags everything, most of the flavors, but including the B. But the B tagging algorithm itself, then we go ahead and use that to identify all the Bs that we use in the analysis, in some further analysis, like a Higgs decaying to BB bar, or to Higgs decaying into these bottom quarks or something like that. So the moment something is in production, is used, we go ahead and actually use that to in the analysis. So I don't know if that's what you were asking, but that was sort of my interpretation of the question. Yeah. I'm not sure I'm following 100%, but maybe we can talk later afterwards. Now, when you say model, now you mean maybe machine learning model, or you mean like the physics model that we use to describe what we understand? The machine learning model. Oh, okay. Are you asking about more of like an adaptive machine learning model that yeah, I mean, all of these guys are actually somewhat adaptive, right, by nature. Now, I guess these recurrent guys also have this idea, right? This idea of recurrence actually means that some of the information gets fed back during the training process. I don't think that's exactly what you're suggesting, but anyway, but maybe we can talk about it afterwards, and you can draw it for me. So. Okay. Any other questions? Yeah. Oh, how is it related? Well, think about it, right? So in this case, you're generating stuff, right? So what we actually have programs which we call generators, right? So what they're doing is, based on some first principle understanding of how, of how these things should be produced, right? So we throw dice and we make different particles, and then these particles they start interacting with the detector, and then we go and reconstruct all that, right? So the point there is that right now we use these generative models at all steps of this process. So the very first applications were, can I actually just produce these particles? Just the particles themselves. Forget the detector afterwards. Can I actually go and generate that, right? And for that, these generative models are excellent, right? And they've shown they're very difficult to train. That's sort of the trick, by the way. That's the part where machine learning community so far hasn't found a very stable way of training these GANs. So there's some issues there, but they're slowly becoming less and less relevant. There's also actually some connection to game theory and things like that, and Nash equilibrium and whatever. But the interesting thing there is that so far, you know, the first applications, they basically generated just the particles themselves, and they show that it's pretty good. The next generation, this is where this LA GAN and also some of the other stuff using Wasserman GANs and so on, they go one step further. They actually go and they try to bypass this generation part, and they go straight from input all the way to the output, the reconstructed outputs, right? And the idea is that, you know, you have basically two competing agents or multiple competing agents with, you know, some feedback, right? And then you also have some tunable parameters that you can change. And what you're doing is you're trying to fool the adversary. You're trying to say, hey, you know, am I making, you know, kind of like similar problem where you're doing like with cats and dogs, but here they're actually particle image detector images, right? The key thing here is, what I didn't tell you is that this is mostly right now for things like, this example is for calorimetry, right? Calorimetry means a problem which you could express as an image problem. So for us, you can take a calorimeter, you know, it's a spherical thing, let's say a cylindrical thing, and you can basically unfold it, and you can make an image, an actual image from the calorimeter, right? And that's why you can make these images. And the interesting thing is that we've been able to do it with all of our detectors, even though they have different geometries and whatnot. You can always unfold it, and you can always make it into this space latent, you know, and then you can use these algorithms to do it. And also with tracks, also we've been able to make track images as well. So and other detectors. But the whole idea, the basic idea is that it's a generative model, right? So it's like you're generating images, or generating cats, or generating whatever, faces. So in this case, the faces are the different particles, right? And in this case, also the reconstructed versions of them. So it becomes like a distortion, right? So in our case, it's a lossy system. So our reconstruction is sort of like, you know, kind of like if you've seen how you try to recover, maybe there was some example that said how you try to recover, you know, the full image from these, you know, kind of like a distorted thing. This is something connected to that too. So yeah. Okay. Other questions? No. Then I think we are a few minutes early for the break, but I think it's okay. We can have a break. Yep.
demasiado... Pero digo, si llega alguien, o sea, hasta llegar a converger a una solución.
Pues redes neuronales por sí mismos, de poco a poco se van así haciéndolo cuando lo haces. Entonces ya, si lo aprendió, ya está dentro de... No es ninguna información extra. Porque fue aprendida por ese mismo network.
Sí, yo cuando veo cómo sacan los objetos, los clasificados, digo, si esos los metes en la red.
Pues si es la misma red que lo aprendió, no va. Sí, pero hay algo que se llama Dark Knowledge. Ahí uno puede tomar una red más fácil. Tiene no más fácil, pero que tendrá... que tendrá... que puede, una red diferente que puede aprender lo mismo que aprendió la otra red. Se llama Dark Knowledge. Sí. Sí, puede ser.
Recursivo en el sentido de que nuevos elementos clasificados por una red, los nuevos elementos, sí, y mejores cada vez la clasificación hasta que ya converjas a...
Ok. Sí, puede ser. Sí. No, de nada. Ok. Okay, let's, wait. Okay, so let's get back quickly to what we're doing. So we're actually going to switch tracks, right? So we're going to go from applications to, we'll go back to maybe a little bit more to where we left off yesterday. There's not a lot of time, and I do want to give you some time to actually play with these tools. So I'm going to maybe skip some things and go less in depth in some of them so that we do a little bit more practical. So just a quick recap, what did we cover last time? We talked about artificial neural networks, right? We talked about their structure. We went over what the structure was. We looked at the different activation functions. I haven't talked about all of them. We looked at how they work, what's the structure, the neurons, the synapses, the network weights, that this is an adaptive system, and you adapt the weights in order to reduce the errors, right? So in this case, the inputs go left to right, the errors go back, so right to left, and you do it iteratively, so in epoch by epoch, you're learning, and you're reducing the errors. So what you're taking derivatives, right? You're doing derivatives with respect to the weights, and then you adjust the weights. So basically, this was that competition, the same thing I was talking about earlier, about the human performance and the deep learning effect. So anyway, 2016 it was already down here, 17 is even lower. So you can see this is a big deal. And simple, you can think of these things, first of all, what we talked about last time was also more like fully connected architectures, right? Everything connected to everything, right? And that's there, you can think of them as more general purpose, right? You can throw them at anything. Right? So these guys are also going to do feature extraction, all that stuff, but they have their limitations. The limitations are that in some use cases, there'll be other types of neural networks that are more natural for the problem. So, but you can also throw this guy in there also to work at that problem. So again, inputs, hidden layers, everything connected to everything, and then the output. And then the output itself can vary depending if you're doing regression or classification. So if you're classifying, right? Then you want to have multiple classes as your output, or you want to be able to identify those. If you're doing regression, estimating continuous function, then that in itself is going to be now a continuous number. Okay. Now, what does it actually mean, the whole deep learning thing? It doesn't actually, what does it mean? It means more complex things, right? So it means that this was like a shallow network of the 90s was pretty simple. A deep network is like that, but it's not just deep. I guess there was a question yesterday, but just to reiterate, it's not just that we made these guys deeper, right? Just making something deeper doesn't make it work, okay? Now, there are some algorithmic improvements that happened over the last, whatever, decade that allowed for these guys to be useful, right? And part of it was there were some problems which people have encountered. And one such problems, let me just sort of summarize the idea. The idea is that now you're training a more complicated model, right? There's an increased depth, large width, there's more feedback and convolution, there's new activation functions. And the other problem is that you want to avoid overfitting. This was an issue which plagued some of the models earlier, is that you had this problem where at some point you stopped learning, right? You started to overtrain. and you have to stop early or find ways around it. So people have found ways, effective strategies to avoid this, to keep taking advantage of more data, of more information, of more learning. This was another big part, has to do with this regularization. Now, one of the new things one of the important things was there was a problem called the vanishing gradient problem. I think we talked about it yesterday. I won't go back to that. But the point is that if you take derivatives of smaller numbers consecutively, chain rule, freshman calculus, what you remember is that it's going to quickly go to 0. So it means that even the larger networks, right? These larger networks like this, they stop training after you've done these few derivatives. They stop learning. So to make them learn, you have to change. You have to go away from these sigmoids, these functions that had these, unfortunately, these undesirable properties of the derivative, to things like ReLU, these rectified linear units. And as was mentioned in one of the other talks, there's different types of these, leaky ReLUs or whatnot. You'll probably hear that. But the nice thing about it is that, first of all, it's faster to take derivatives, but also it avoids this vanishing gradient problem just because of how it behaves over here. Right? So now you can take derivatives, you can actually learn from the data, even with wider networks. And this was a big breakthrough, a big deal, even though you still train it by backpropagation. This was one ingredient into this revolution, is the ReLU. Now, the other part is this regularization. I'll just give you one quick example. And I guess I mentioned that in my talk just a little bit earlier, that there's something called dropout. And the idea of dropout is that, this is just one example. Now, not everybody uses dropout anymore, but dropout as an idea is something interesting. So the idea is that even though you have a fully connected network, right, or something like a fully connected network, at each epoch, right, when you're training the thing, you can actually choose to randomly drop some neurons, right? And the effect it has, it allows you to avoid getting stuck, right? So when you're doing the sort of gradient descent or whatnot, it helps you avoid getting stuck in these local minima if you want. And then continue learning. So it's a form of regularization, right? Which in itself is also connected to some Bayesian ideas that I mentioned, variational inference. So this is a nice thing. This is also another thing that allowed, one of the things that allowed us to train deeper and train better. So it's a learning improvement. And anyway, then there's also other types of networks which have appeared, also to address certain types of problems. So for example, like convolutional neural networks had a very nice property that now, in addition to sort of this fully supervised, fully connected thing over here in the end, you also have not everything connected to everything, and you have also some unsupervised learning and some feature extraction happening in some of the first layers. It works kind of similar to how our retinas work and whatever. And they start with simple features and getting more complex, and eventually getting to sort of more fully connected architecture. So the point is that these guys have been really good for image type problems and other types of problems. And if your problem is an image, you really should go in that direction. Now, there's been other types of architectures. For example, like convolutional neural networks have been used for feature extractions, for whatever, numbers, and you've seen examples in particle physics, how we use them. You've seen them in astronomy. You've seen in many things. If you have images, these guys are the way to go. We've been working with, these convolutions. They're n-dimensional things. We've been working with convolutions of various dimensionalities. So 2, 3, higher. And the point is that depending on the problem, you can figure out what's the proper architecture. Now, recurrent neural networks are another types, and this is the point. Let's say you also have a time dimension that you care about, or something like that, right? You have an evolution, like I was talking about tracking for us. We have to keep time as the object evolves, as the time goes on, right? You need to keep track of that. So these guys kind of incorporate that idea into the network. Another idea is they try to do the same thing. They use complex valued neural networks, and they introduced phases, things like that. But this is a different idea. This actually introduces the cyclical part into the network. Now, just to give you an idea, okay, I like this little thing. Now it tells you kind of like, this is the feed-forward stuff, right? That kind of, the guys from the 90s, and even today too, people use them. But then everything else, what people are starting to use now, a lot more of these guys. But this stuff is lurking out there, right? There's some nice fundamental ideas which are all around that are not necessarily at the forefront of what everybody's applying, but some of these ideas are coming up. By the way, I haven't added GANs into this picture and whatnot. Some ideas just sort of just show up, and then a year later they're everywhere. So this is one of those cases. So anyway, so this is just to give you an overview of where things are in this. Now, obviously, performance-wise, on something, this is that Higgs machine learning. Somebody asked me in the back about this Higgs machine learning competition or whatever else. Here, this would be what you would get with a boosted decision tree, state of the art, maybe 10 years ago. A deep neural network will give you a significant improvement on this in this ROC curve. What's really interesting as well is you can see that if you use like a shell network and you give it just the low-level features, the low-level stuff, just the primary basic stuff. If you train a shell network, that's the worst. If you give it also high-level features, like engineered ones, like physics domain knowledge, you put in all your knowledge from theory, all you can, and you build, and then you apply a shallow method to that, guess what? You do better, right? You do better. So great. Yay for the engineered features, right? And then, look at this. The red and the black are on the same. And that's the deep neural networks. Now, that's the deep learning guys. Even just the fully connected, forget the convolution and all that, just the fully connected guys working with just the low-level information are able to just as well as the ones that had the low and the high. What does it tell you? It tells you that that network is capable of extracting those features and taking advantage of them. So that's why feature extraction is a big deal in this context. So this is just a simple example of this. So very quickly, I'll talk about function estimations. And this idea is not new, right? This is still from the time of Gauss when he figured out how to, this fancy idea of regression about the comets. But anyway, the same idea. The only thing you do is you change the induction algorithm. You change your evaluation. So instead of trying to separate things when you classify, you're trying to achieve minimal variance. Because what you want to do is you want to split the parameter space in a way that within that parameter space, things are changing very little, right? So you can assign some value to it. That's the idea. And at the same time, you want it to be as far away as possible from the others, so from the other values. So that's basically the idea in the regression. So here's an example from particle physics, actually from the Higgs to gamma-gamma discovery thing. So for example, if we use the inputs like where the photons are, some sort of information about the event, and in this case, your output is like what's sort of the true energy is. And what you see is that, you do much better with this sort of machine learning estimate of even in this case, just a single output regression. You end up doing better. And, for us, better means more narrow, more close to where the Higgs should be. So that's kind of the effect it has, about a 30% improvement. And that's just a simple BDT. This is somewhat old now. Nowadays we use deep learning for this same thing, and the improvement is another significant amount. So actually, here's the deep one. I'll show you the deep one. So you see, here you want to be higher and narrower, right? This is just a simple deep neural network with just a few layers. So one hidden layer is the guy over here, the red. This is basically equivalent to this BDT, the boosted decision tree. That's him. But then you can see that as you start all you're doing is just increasing layers. This is not even a sophisticated guy, it's just a fully connected network. You see the resolution's improving. You add other things like convolution and so on, and it starts to go even higher. So anyway, just to get an idea that deep learning, even in the context of regression, also has a lot of benefits. So. Okay, now multi-objective learning. The last thing I'm going to say, and then I'll let you guys have some fun, the practical stuff. And the idea that sometimes you need to worry about multiple outputs, multiple targets, right? And for that reason, that multitask model I was talking about right before is irrelevant. Now, multitask model could mean multi-class classification, or it could mean multi-target regression. Multi-target regression is when you're trying to estimate at the same time a number of functions simultaneously that maybe even depend on each other based on the input. So the inputs could be, and there's many applications of that. But the point is that you have, this is a simple example, some simple example. You have some bunch of inputs, some of them strongly correlated, a bunch of outputs. And your challenge is to build a predictive model that's going to simultaneously describe all the outputs correctly. Getting one of them right is not enough. You need to get all of them right. And the point is that this shows you actually that you can do that with some of these methods. And the idea is that you get very close in your target and prediction. The critical thing to worry about there are the correlations. Remember, 4 of them were very correlated. What you want to learn are the output correlations. Right? That's your test. You want to see how well they're actually learned. And what it tells you, you can actually make a difference between what you predicted and what the target was. And you can see they're essentially 0. So this model works. And this is a deep model that does that. So the point is that if you have a task that requires simultaneous estimate of number of functions or number of parameters, it's possible using these machine learning models. Okay, so I'm going to stop here and see if you have any questions. And I think we're going to go and have some more fun with Swan and Binder. Any questions? No. Okay, so I think we're going to have to do the same thing we did yesterday, since I guess we have quite a lot of people again. So I'm going to go and I'm going to ask you guys to maybe go in pairs, right? And I'll give you a number, and that'll be your login into Swan. Use that number. Today, so remember last time we did Swan, and I promise you that today we're going to do Jupyter Notebooks, but I'm also going to give you other options, so like Binder. If you look at the agenda of today, I've linked 2 tutorials. So you're going to have a choice today. Everyone's going to have 3 choices today. You're going to be able to log into Swan, and remember we had all these notebooks. You can try all these notebooks for TMVA. That's one of those toolkits that has different machine learning algorithms in there. That's one of your choices. The other choice that you have, I also added another tutorial, two other tutorials for you. One that has to do with TensorFlow and Caris, and which is there, and another one which is going to be using for PyTorch. So those of you who always wanted to try PyTorch, you can also try that. So, and that's you can use that with Binder. So all of you will have a choice. You can make the choice. You can try one of them. You can try a couple of them. And once you start, give them all a try. And I'm just going to kind of walk around and try to answer your questions. But I would encourage you to actually go and try these. And if you get stuck, you can ask a question. I think there'll be a few other people here who can help you. So your choices are, so let's first log into Swan anyway. So I'll give you all logins. So one, actually maybe, can you guys work together? Okay, in that case, 1, 2, 3. Can you guys work together? Yeah. 4, 5. You're 4, you're 5, you're 6, 7. You need to find someone. So, is there anyone who needs a partner? Oh, maybe that. Can you guys work together? Okay. I think there's. Somebody from. Well, these guys are gonna work together. So maybe can you go over there with one of them? Yeah. Okay. So what do we say? 7, right?
1.
Oh, you're 7. Okay. Okay, you're 7. So you're 8. So they're 1, 2, 3. Okay, so you're 8. 9? New number today.
New number.
9? Yeah. 10, 11, 12, 13, 14, 15, 16. Okay, so 16, 17, 18, 19, 20, 20, 21, 22, 23, 24, 25, and 26 in the back. Yeah.
Should we log in with mlearn?
Yeah, I'll put that up again. So I'll put that up again so you can see the logins. Okay. So, okay, you already seen this about Jupyter, Swan. Yeah, so your usernames are mlearn, whatever number I gave you, and then the password is mlearn at that number minus 1. Okay. No, here. Don't worry, it's going to be there. Yeah. Okay, so then what was your, I think, you can be number 28. Oh, actually, wait, were you guys number 1? Can we change to number 29? 29, okay, I forgot that I need to use 1 myself. Okay, yeah. All right, did everybody manage to log in? 0, 9. Sorry, so if you're between 0 and 10, then you are 0, 7, 0, 8, whatever, 0 something. Regression. Okay.
Hay una dependencia en la escala de regularización, ¿no? En los procesos.
¿A cómo se obtiene la escala con el regression?
O sea, ¿cómo se definen las escalas de regularización? ¿No?
Regularización es otra cosa. Porque en el regression, bueno, en el regression también puedes introducir regularización. Entonces la regulación es algo que se introduce para que el modelo se hace behave, o en este caso para que no haces overtraining o algo así. Pero en regression también, pero también puedes introducir como regularización o algún penalty o algo así. Entonces no sé cuál caso estás pensando. ¿Ya?
Porque pusiste el caso de redes neuronales y después el otro que era el caso de
BDT o algo. ¿De cuál? ¿Tienes el slide en específico? Sobre el classification a lo mejor. ¿Estás buscando del hoy? ¿Uno de hoy? No, ese no es del hoy. Del hoy va a estar... sí, está aquí. No, perdón, que mi slide todavía no he puesto. Ok, pero... bueno, déjame mirar primero que todos van haciendo login y después miramos. Sí. Okay, everybody in? Okay. So that means, actually, before I'll just tell you quickly, there is this, one of the things you have there are these notebooks from TMVA. That's like a particle physics workhorse, so to speak. It uses root and it's used by our experiments. But anyway, it's got a bunch of stuff and it's got like different notebooks. So you'll see, like, I'll actually show you when I log in myself, I can show you what is there. First, I'll tell you what's on the menu and then you can pick and choose whatever dish you like. But let's first of all look at what's on the menu. So, let me log in myself as well. Okay. So, mlearn01. By the way, does anybody have any problem logging in? If you have a problem, raise your hand. Okay, no problem. mlearn at Okay, so when you logged in, you should have gotten to this screen. Swan. So Swan is like a Jupyter Notebook service, right? And here, what you should choose is, we're living on the edge, so we'll use this development bleeding edge, which might be unstable. So we're living risky, Anyway. So here, if you go, CERN box, as I think I mentioned yesterday, that's like the CERN version of Dropbox. So here you can go to the tutorial UNAM, and here you will see that there are a bunch of notebooks, right? We went yesterday about how to use Jupyter and all that stuff, right? So here you will see there's a bunch of these notebooks start with TMVA, and then you have something like data loader, it tells you how to deal with the data, CV's cross-validation, DNN, that's deep neural networks. There's one on Caris, because within TMVA also has interfaces to everything. So it has interfaces to scikit-learn, Caris, to TensorFlow. So you can just work within TMVA if you like. So you can actually have a look at this TMVA Caris examples of classification and regression. Let me just open that, for example. And what it's going to do, it's going to open you a notebook. Well, it's going to think first, and it's going to open you a notebook, and then you can actually try this. So, which notebook did I click on? It's called TMVA Caris Classification. So, what that's going to do is you're going to basically instantiate like a Caris model, a simple Caris model, and you're going to produce an output. So, what you can do is actually clear the output. The way I do it, usually go kernel, restart, clear. You need to wait for the thing to say kernel ready. Only when it says kernel ready is when you can start doing stuff. Sometimes it dies, don't worry, just refresh. Yeah, now it's ready, okay? So now you can actually start using this thing and go Shift-Enter. Now it's thinking. Whenever it finishes, see it says welcome. Okay, it's going to use TensorFlow, backend. And then here you can continue. You can kind of like go one by one and try to figure out what each one does. You know, that just tells you what the output file is. You know, that you're going to do classification. Here you define your signal in the background, your two classes, for example, and then you prepare your data. And then after that, you have your model. You see, this model is going to be a sequential model. You're going to add basically a dense layer and a layer of neurons, and then you're going to have a softmax activation on the very end. You see the activation function is ReLU, and that's your model, right? You see, pretty easy. And then afterwards, you can compile, and you can book other methods to compare with. Actually, let me just go through this in some here anyway. So let's say you're going to use a special kind of optimizer called Atom, and you care about accuracy. Remember, this is, I forgot, is this classification or regression? This is classification. So here we're going to do classification. And here, just for fun, because TMVA gives you other methods you can compare with, so you can compare like Caris, this neural network model that you just built, that you just gave it, with, for example, another method like the boosted decision tree BDT, or a simple Fisher linear discriminant, just to see how well you do. And then you can click Shift-Enter, you can get an output, it's training, and then here you can say train all methods, test all methods, and that's where all the work is happening, right? That's when it's doing all the training for all these guys. And then when it completes all this, then you can visualize the result, right? So it's just a simple notebook, and you can see in this folder, it's still running. In this folder, you have maybe 10 such notebooks for different things, like regression with Caris, regression without Caris, whatever. You also have something like RMVA. If you want to use R within this, you can use that. Variable importance. CNN, that's convolutional networks. So that's what you have in Swan and in those folders. So you basically have that. Did it finish? Yep, it's done. So now, is it done? See, actually it's not done. When it's done, you're going to get a number, but looks like it's almost done. So there, now it's done. You can ignore that warning. No big deal about that. So now we can look at the output of this. So that's going to, open up some plotting. Here. And that's going to show you the ROC curve, which you remember that was the receiver operator characteristic, right? So you can see that, for example, the Fisher is the black. That's the linear guy, obviously the worst, right? But then you can see the BDT is in red, and that's how good you did in this particular case with a boosted decision tree. And you can see that PyCaris, that simple model, we didn't do anything fancy. We just added like like a couple layers, nothing else, outperformed the BDT already. So anyway, you can play with that. Play with all these examples, get familiar, try them all out. So that's your gourmet menu part 1. Okay. Now another option that you have, if you go to the links I added to the event. Sorry, I think I'm in here. If you go to timetable. And you go to Friday here, there's going to be 2 links in there. And the first link is another tutorial, which is a TensorFlow and Caris tutorial. So there's a link to that. It's self-contained. So what you can do is you can basically it goes in depth in Caris. If you want to learn about Caris, you should try that. But just to complete the menu, right? So you have a little bit more options. The second link is going to take you here, and that is a different tutorial. That's a PyTorch tutorial, and that's also connected with simulation. So if you're interested in simulation, that could be something you can try. And that, instead of Swan, it uses Binder. A Binder, it's like an on-demand kind of Jupyter Notebook service. So here, what you can do is you can click this button, which is going to launch Binder. It's going to,
do stuff. It's going to build, so you can see what it's doing. It's the launching server, blah, blah, blah. It's going to take a little bit, hopefully not too long. But that itself is a tutorial of PyTorch. So if you want to try, now PyTorch is really kind of like the latest, greatest thing in deep learning. So I figure I'll give you an option on that too. Although for whatever reason, if we all use the network together, things might get a little slow. So anyway, these are your options. You can pick what you want. But basically, there is a notebook here for GANs. Some of you were asking about these generative adversarial models. This is an example of what you can do there. So basically, this is going to tell you how to set up PyTorch and how to do some of this generative adversarial network. So you pick your poison and give them a try. And then if you get stuck somewhere, just raise your hand, and I'll try to come and help, and maybe a few other people can help too. So, okie doke. Let's try this. Then you need